In this video, we'll be extending the conversation on the randomized complete block design by demonstrating how we add a blocking factor to the one-way ANOVA that we've been previously doing. So if we have A treatments or factor levels, and again, sometimes you'll see this as capital I instead of A, with B blocks, the statistical model, and we tend to use the treatment effects model here for the randomized complete block design is shown in this equation. Now, a couple notes here. We almost always just use the treatment effects model when looking at the randomized complete block design, or frankly anything that goes beyond the simple one-way ANOVA. And that's because that as we start to look at more and more factors, we have to write these mu's with i's and j's, and there's just so many different things to track that it becomes a bit silly to use the cell means model anymore. So we really just look at the treatment effects model. Typically in the blocking factor, we do not have replications within the blocks and treatment combinations. So there's no additional subscript here. We have the ith factor, we have the jth block, but we aren't really accounting for any replications within each block. This is very typical in the randomized complete block design. Finally, for those of you who know what this is, note that we don't have an interaction term here. We're not looking at the interaction between treatments and blocks. We haven't formally talked about interactions, so if you're not familiar with this term, that's just fine. But for those of you who are, note that the interaction term is not part of a randomized complete block design. In fact, we never look at interactions with blocking factors. Remember, blocking factors aren't of interest, so the interaction term with the blocking factor also isn't of interest. The term for a model without an interaction term is called additivity, or an additive model. So additive models are, again, very common or required in the blocking design with the one-way ANOVA adding the blocking factor. We'll always have this additive model. So the fixed effects hypothesis, we're assuming that this null hypothesis, all of the means are the same. And then the mu sub I, this is the average treatment effect across all of the blocks. We're literally taking the average across all these J's, is the average of the mean of that treatment group across all the blocks. So we're assuming that all of those averages are going to be the same. Now, in the same way that we partitioned total variability before, we can do the same thing again, but now we've got multiple components that we're tracking in addition to error, and this error term becomes very, very yucky. So breaking this apart, we have this full term, and we're going to split this up just like before. Note that when we have this b times the sum from I equals 1 to a, remember this is a double sum j from 1 to b. We just don't have any subscript j's. In the same way, this is also a double sum a from I equals 1 to a, but we just don't have any sub i's in this case. So we drew this out previously in class, but note that in these cases, these can both be written as double sums themselves, and it tends to be a little bit more convenient that way. Now for this case, this is our error term, and we're going to come back to this term at a later point, but this is a very, very yucky term. So when you're thinking about the sums of squares treatments, that's this term, the double sum over I and j of y sub I dot bar minus y sub dot bar quantity squared. This matches almost exactly, actually this is exactly what we had before. The sum of squares for blocks is exactly what we would think it would be. It's the y dot j bar minus y dot bar quantity squared. So this is the difference between each of the blocks and the grand mean and the double sum over all that. So this is exactly what we would have normally expected for the sum of squares of blocks. The sum of squares of the error, though, this is the weird one. This is just kind of the remainder of that equation. Again, we'll come back to this term at another point, but we take each individual point, subtract both the treatment mean and the block mean, but then we add the grand mean and take that quantity squared and then double sum it. Now, just like we have the sums of squares that are all able to be added up, the degrees of freedom are all able to be added up as well. Now, for the degrees of freedom, remember our total degrees of freedom are going to be that AB minus 1 or IJ minus 1, capital I, capital J minus 1. In the sums of squares treatment, we have little a minus 1. The sums of squares of blocks, we have little b minus 1. So this little a minus 1 is what we had before. This is what you would expect. And same thing with the b. We have b blocks, so we very well expect for the sum of squares blocks to have b minus 1 degrees of freedom. Then the sums of squares for the error is the a minus 1 times b minus 1 quantity. So that's a little different than we would normally expect. You could also remember just find the sum of squares of the error by taking the sum of squares of total and subtracting out the sum of squares treatment degrees of freedom and then the blocks degrees of freedom. So having already defined these on the previous slide, we'll just write in sum of squares treatment, sum of squares block on all these slides. Your mean squares are going to be the exact same thing. We'll look at some of the manual computations. Again, I personally just use those double sums when we're working through R. I think that keeps it easier and goes with the definition. I think we have the manual computations on the next slide. Looking at this slide, again, this is exactly what we'd normally expect, and you'll want to fill in these sums of squares treatments and blocks and errors with what we had a couple slides ago. The mean squares is exactly what we would expect, but the F ratio might surprise you a little bit because everything with the blocks, this is our new row in this ANOVA table, has really kind of mirrored what we've done with the treatment. It's been a slightly different version of the treatment, just applied to the blocking factor instead of the treatment factor. The degrees of freedom are the number of levels in the blocking factor minus 1, same as the degrees of freedom for the treatment, the number of levels in the treatment factor minus 1. Mean squares are the same, sum of squares divided by the degrees of freedom, but only the treatment has an F statistic. And think about for a second why. Remember that when we're using a blocking factor, we have declared that the blocking factor is a factor that is not of interest. We are not interested in the contribution of the blocking factor to the dependent variable. We just want to know the blocking factor is related to the dependent variable, but we don't really care anything about is it statistically significant. We're not doing any statistical tests at all. One of the reasons we're not doing any statistical tests is because this hasn't been randomized. One of the big pieces that separates an experiment from an observational study is the randomization control, and blocks haven't been randomized. We've done randomization within blocks, but not across the different blocks. So that restriction on randomization really limits the conclusions that we can make about blocking factors. There are different opinions on this, but traditionally you're not going to see a statistical test of a blocking factor because, again, by definition, the blocking factor is not of interest. We're just interested in the statistical test of the treatment factor after accounting for block. Incidentally, that's how our conclusions will be phrased, is the effectiveness of the treatment after accounting for block. That's what our statistic is going to determine. So obviously we'll be using software to analyze this. I, again, use those previous equations, and then, of course, you're going to get to try one by hand on your own, and then use the built-in software for the rest. That'll be the next video, or in a couple videos, depending. So again, this is the manual computation stuff. I'm not a big fan of these manual computation equations. If you had to do it, like if you're writing it out by hand, these might be nice. But when we're taking advantage of this in software, I actually far prefer to use the definition because it better allows you to see what's going on when we're partitioning those sums of squares. Now, one thing I will point out about this is that even if you're using the manual computations, sometimes it's just easier to, after you've found 3 of them, find the 4th sum of squares component by subtracting the other ones to find it. So once you found the sum of squares total and then any 2 of the treatment blocks, the error, you can find the 3rd one of the treatment blocks and error by just subtracting the two that you have found from the sums of squares total. This is nice when you're using these manual computation equations, and that's why they're on here. This is also nice even if you're using those definitional equations from a few slides ago that I prefer, because remember that one for the sums of squares of error was just really, really nasty. Y sub ij minus yi dot bar minus y dot j bar plus y dot dot bar quantity squared double summed over that. That's a pretty nasty term to have to deal with, so this can be an easier method. Now for our assumptions, all of our assumptions are the same. So when we're looking at these assumptions, every single one of them is the same as our one-way ANOVA. That is, we still assume independence within the context of the model. And remember, we had a long discussion about independence and what that means. Normality, the homogeneity of variance. And thinking about this, we still have an error term. The distribution of the error term hasn't changed when we're moving models. So this error term is still following all of those things, that normal with a mean of 0 and a constant standard deviation being independent. But that said, so this is our starting place, all the same assumptions. But when we add in a blocking factor, we have an additional assumption. That additional assumption is that there's no relationship between the independent variable and the blocks. That is, that there's no interaction. And we mentioned this earlier, this is an additive model. Maybe something to think about is looking at that coupon example that we talked about earlier with the testing tips. We want to make sure that it's not like maybe one of the tips and one of the coupons were magnetically related. So something weird happened when you put those two things together. That's what we would call an interaction effect, that when you put a level of the blocking factor and a level of the treatment factor together, something weird happened or something different happened than we would normally find. Our assumption in a randomized complete block design model is that that is not the case. Now, incidentally, this is our assumption in all additive models, and this is our assumption in all single replication models by definition. But here we're assuming that there is no relationship between the independent variable and the blocking factor, that it's just the independent variable related to the dependent variable and the blocking factor related to the dependent variable, and that the independent variable and blocking factor don't affect each other in those weird ways when you combine them. So real quick, let's go through an example together. So we're going to be looking at vascular grafts and a whole bunch of different medical stuff that, frankly, I don't particularly understand. But what we want to see is that the extrusion pressure affects the occurrence of flicks. Okie dokie. There it is. But we've got this supplier that we need to account for, and we think that the batches in the supplier might have an effect. So this is going to be where we have the blocking factors in that batch. All right. So we have conducted this experiment, and now this is a data table. Again, I tend to make my blocks as the rows and my levels of the independent variable at the columns. The book tends to do it the opposite for me. Pick your favorite. So we're really looking at this pressure and how it affects the medical outcome of interest. And we just want to account for the batches of this material that are coming in as we're looking at the relationship between pressure and that medical outcome. So first thing to note, that within each of these blocks, we have randomly assigned to run each of the different pressures. So remember, we had that random assignment table that we looked at in the previous video, and we said this is not how you would present data, but this is a great way that we can organize randomization. So this is the opposite. This is how we present data, but in presenting data this way, this does not represent the way in which the data were randomized. So we'd have to go back to that randomization chart. We'd have to kind of create a randomization chart here if we were looking to create a randomization chart to represent the randomization of each of the pressures within blocks. So that's something that we need to acknowledge here, that for each of these blocks, it wasn't that the 8500 psi, the 8700 psi, the 8900 psi were run in that order. That's not the case. They were randomly ordered within each of the blocks and run in that way. So we finally have our model, we have our data, so we plug it all in and interpret the model, right? No, remember, the first step is to check the assumptions in all of our models. So don't get tricked here. But we calculate the model. So the textbook obviously uses a different software, but in R we would fit the model, and then we immediately, before pulling up the model, before calculating a summary of the model, before looking at p-values, immediately we go in to look at the assumptions. Looking at this PP plot, this looks absolutely reasonable. This looks fantastic. The plot of residuals, so this is our determination of seeing if we have anything like lack of homogeneity of variance or anything like that. This looks fantastic too. We've got the different residuals by each of the pressures. So this is by the independent variable, seeing if all of these have equal variance in the independent variable. That looks good. The batch of raw material, that looks good as well. Note that when we do it by this predicted, this is a conglomeration of both the blocks and the treatment level. So this is a little different than what we've looked at previously, where we could just calculate a histogram. And here we're looking for a nice random spread with no patterns, but we can also do it specifically by our treatment levels and by our blocking factors to make sure that homogeneity of variance within these factors is met. So this all looks fantastic. And because of this, we can go on to interpret. So summarizing, the basic residual plots indicate that normality are satisfied. And again, that's not we have proof that we have normal data and constant variance. It's that we didn't really see any problems. Didn't seem to have any obvious problems with randomization. There wasn't any patterns in the residuals. We could also do a residual plot by the factor, which we did and looked at. And again, these plots talk about potential outliers, but because we look good, we can go on and continue with our analysis. So the textbook does it using these by hand equations. Again, mixed feelings, but you can do what you want. So we've got the sum of squares total, we got the sum of squares treatment, we got the sum of squares blocks, and then the textbook uses the sum of squares total, treatment, and blocks to calculate the sum of squares error. To calculate our mean squared, we simply divide the sum of squares error by its degrees of freedom and the sum of squares treatment by its degrees of freedom. And then once we have the mean squared error and the mean squared treatment, we find their ratio. Looks like their ratio turned out to be 3.29. Looks out their ratio turned out to be 8.11, and the F critical value turned out to be 3.29. So recall that what we're looking for in our statistical test is that our test statistic 8.11 is greater than the critical value of 3.29. Because that is, we conclude that the pressure does affect the yield of this statistical test after accounting for the resin. So we can determine that this is statistically significant after accounting for this resin. Now the book goes on to do something kind of interesting here. It discusses the blocks, and you might find this interesting because thus far we've been saying we really don't want to look at the blocks. However, we do want to look in general at the variability of the blocks, the sums of squares and the mean squared, and we could even look at variance components here too, because we want to see, are the blocks worth accounting for next time? So if the blocks don't have any variability associated with them, then it's not even worth bothering to account for blocks in the next experiment that we run. And remember, if we're including a blocking factor that has very, very, very little variability in the dependent variable associated with it, that blocking factor can actually reduce our statistical power. It can increase error because we added it to the experiment. So we do want to keep an eye on the amount of variability that blocking factor is accounting for. We can do this by loosely comparing the mean squares from the blocks to the other mean squares. And we see that the mean squares for the blocks, at least the sum of squares for the blocks, and if we divide it by its degrees of freedom, I guess we can do this on the next slide. So the mean squares for the blocks actually does not seem to be particularly small. So we look at the mean squares for the error, that's about 7. The mean squares for the blocks is about 5 times the mean squares for the error. That's a reasonable value, indicating that the block is accounting for a large source of variation. Now remember what would happen if we didn't include this blocking factor. All of this sums of squares component would go back into this residual. Now so would some of the degrees of freedom, so it would balance out a little bit. But ultimately, this would increase our residual sums of squares if we didn't account for the blocking component. So accounting for this blocking component is a very important thing that we did. And again, it greatly seemed to reduce our residual mean squares or a mean squared error. So we see our F statistic. This is just the ratio between the mean squared error from our treatment and the mean squared, the mean squares of treatment and the mean squared error. So that's our 8.11, and then the p-value was calculated via software for interpretation. In this software, it looks like this is Design Expert. It even gives us a R-squared and adjusted R-squared, so we can determine that the treatment and blocking model, the model that accounts for treatment and blocking, accounted for about 61.85% of the variation in that outcome. Typically, I guess we'd use adjusted R-squared, so about 54% of the variation in the outcome is what we'd expect it to do in a future study. Now this is presented in a different software. I think even we have one more coming up here, but we still see the same F ratio, the same contribution. Now note that sometimes in some software, the batch, even though it's considered a blocking factor and we've designed this to be a blocking factor in our design of experiments, the software doesn't necessarily know this. So the software still gives an F statistic and a p-value, even though we're really not interpreting these. So these, because of the randomization procedures, and depending on who you listen to, may or may not be interpretable. Frankly, I might look at this to see, hey, should we bother including this blocking factor in the future? I might not. But as a rule, we tend to not want to interpret this. So when the statistical output, if it gives you a statistical output for a blocking factor, just kind of mentally cross that out in your mind. Unless you're looking to see if the block contributed anything, to see if the block should be included in a future experiment. Now note that once we've done this, we can still compare. So we found a statistically significant difference. So now we can do our pairwise comparisons to figure out which treatments are different. Note that you could also do something like box plots next to each other to help get a visual of this. But our statistical follow-up, and remember in the textbook they always use the Fisher's LSD. In our class we've talked about some other probably better options in this particular case. So treatment 1 versus treatment 2, it looks like treatment 1 and treatment 2 are not statistically significantly different, p-values 0.47. Treatment 1 and treatment 3 look to be statistically significantly different, but this is an unadjusted. So actually adjusted, this is probably not going to be statistically significantly different once we've adjusted for the number of tests. Might be borderline, so maybe 1 and 3 are different. Maybe not. And the mean difference, 1 minus 3, so it looks like 1 is going to be higher than 3. 1 versus 4, very statistically significantly different. Looks like 1 is going to be higher than 4. 2 versus 3 doesn't appear to be statistically significantly different. 2 versus 4 does appear, so it looks like 4 is just way lower than these other ones. Everything in comparison to 4 seems bigger, except for 3. 3 and 4 looks like 3 is not statistically significantly different than 4. Though it's close, remember that this is an unadjusted p-value. So even though this one's close, if this were an adjusted p-value, I might make a little statement about how this one's close and it's worthy of future research or whatever. But because this is unadjusted, this would only get bigger as we made the adjustment. So as we're looking through these, it's important to realize that even though these are statistically significant, let's use the very statistically significant one, the difference between treatment 1 and treatment 4. That does not mean that a mean difference between these groups is practically significant. So to interpret this, I'd take this to a medical professional. I'd say, hey, your vascular graft gave you a difference in whatever 7.05 between these two levels of the vascular graft. What do you think about that? And if they said 7.05, OMG, that's just the most amazing thing, well, then this is going to be both statistically significantly different. That is, we have evidence that this difference is not zero in the population. And this is going to be practically significant. That means that it sounds like medical professionals would walk away changing practice based on this number. Now, it could be just as well the case, and this happens far more often than people acknowledge or realize, that I come in with a statistically significant difference of 7.05. And that means that a statistically significant difference just means I'm pretty confident that this difference is not zero. So when I say statistically significantly different, I just mean this difference isn't zero. That's all I'm saying. Doesn't mean it's big, doesn't mean it's small, it just means it's different than zero. And if I take this to a health professional and say, hey, the difference between treatment 1 and treatment 4 is 7.05, and they say, that's it? I wouldn't do anything for 7.05. If I go lift my right arm above my head, I get a difference of 7.05. That doesn't really mean anything. Then even though this difference is statistically significant, it might not be practically significant. That is, it might not be worthy of pursuing anymore from the practical side, just because nobody's willing to do that or nobody cares all that much. Think about if it costs $1 million to raise somebody's GPA by 0.001 GPA points. That might be statistically significant. In fact, if we had a large enough sample size, we might be able to conclude that if you did this $1 million program, it improved your GPA by 0.001 statistically, not prove, but provide evidence of. And statistically, we might have enough evidence to believe that that's not going to be zero. That said, just being different from zero is not enough. If it's 0.001, if it is that small, even if we have evidence that it's not zero, for $1 million, it is not worth raising your GPA by that small of an amount. So in this case, we could go to an expert to supplement our statistical significance and determine, is this difference practically significant? Or we could come up with a confidence interval, ask them to interpret the top and low ends of the confidence interval, that reasonable range of this difference, all possible options for interpreting these kinds of differences. All right, so some other aspects of the randomized complete block design that we're not going to talk about. We already talked about that the randomized complete block design is an additive model. That is, there's no interactions. We haven't talked about interactions yet. We actually talk about it in the next chapter. It's kind of this catch-22. We'll just deal with it. So we have an additive model, and additive means no interaction, whatever an interaction term is. We should note this is an assumption, but this isn't always true. And I think the textbook goes a little bit in depth as to how you could try to find this. There's a couple of different methods that you can use. But it's important to realize that this is an additional assumption. This isn't a conclusion, but this is an assumption. Incidentally, anytime you don't include an interaction term in a model, you're adding the assumption that there is no interaction term. You're forcing the interaction to be 0 in the model. So just be aware of that in more general modeling, in the more general modeling world. All right, so treatment of blocks is random. Again, we're not going to talk about this super much. We've got this on the next slide quickly. In fact, we already talked about random effects models. It's not going to be that different from what we've already talked about, save we're going to add blocking to the mix. But there's many more details in the book. Check that out if you're interested in. And finally, the balanced incomplete block design or missing observations. We're not going to talk about this at all in this class, but the balanced incomplete block design, the BIBD, is probably one of the most interesting things that we're not going to talk about. And it has to do, we talked earlier about like, let's say we were doing 4 tips and then we got coupons, 4 coupons from a single ingot of metal. We went through this together in the previous video. In that particular case, what if we didn't have, what if the ingot only gave 3 coupons of metal? So what if in chopping up the ingot, we had 4 levels of our independent variable, 4 tips that we wanted to test it on, but we could only get 3 coupons. So we couldn't get enough experimental units from the block to give an experimental unit to every level of our treatment factor. What do we do then? And that is the balanced incomplete block design. It's a very interesting design, something definitely to check out. The analysis is going to follow very similar to what we did, but how you design it is a little bit different. And again, our textbook has some details about that. All right, so we're going to quickly go over this random blocks. I should first say that this is going to look very familiar to what we already did with the random effects ANOVA, save that now we also have a blocking factor that we're considering. So note that we have the expected value of the mean squares treatment with our sigmas. This is kind of what we had earlier. But now we also have the expected value of the mean squares of the blocking factor. And we have this variability of the blocking factor at every single level of the treatment level. So this is A, the number of treatment levels times the variability of the blocking factor. Same thing with our treatments. We have the variability of the treatment effect at every level of the blocking factor. So this is B times all of those different treatment effects, something to take into account. So our appropriate statistic, note that our variance components from the one-way ANOVA are the same. Here we're just specifying the variance components for the block, this sigma squared sub B hat. So this is the mean squares blocks minus the mean squared error over A. This is very similar to how we found the variance component for the treatment earlier, and you can go back to the previous chapter to check on that. And we simply do this calculation to determine the variance component that's due to the block. And then we can calculate, well, how much of that variability is from the blocking factor. So here we can look at our variance components, determining how our variance components line up with the blocking factor, the residual, and then the total amount of variation. We can also compare this if we want to. So in this case, this is just all of our blocks being assumed to be random. So we can see that the variability from our blocks is roughly equal to the variability due to error, a little bit more even. So this variability due to blocks is quite meaningful. It's taking about half of the variability of the total variability away from that error component. That's a very, very good thing. Now this ends our conversation about the randomized complete block design. In the next video, we'll move on to actually this will be the next section of the course. We'll move on to the randomized complete block design with 2 blocks. So we've been talking about how do we add a single blocking factor to that one-way ANOVA. How do we add a block onto that? Now we're going to talk about how do we add 2 blocks onto that, and that's got a special term called Latin squares. So you can look forward to that coming up.